EDX Decision 1, Graphs and Networks 2, Shortest Path and Route Inspection. Shortest paths. As a little warm-up exercise, you could pause the video here and see if you can find the route from A to F that has the least total weight. We will look at a solution and an algorithm for this problem in a short while. The best analogy for this algorithm is to think about a taxi journey where you want to find the shortest route from your pickup point to your destination. So we may have a network of locations and we want to find the shortest distance, or in some cases the shortest time from one location to another. Some algorithms will solve both of these problems. One case considers the network of distances and the other the network of timings. The shortest path means to find the path of minimum weight. The weights of the edges may be distances or times, or perhaps depreciation costs or petrol charges, etc. We will be using Dijkstra's algorithm from 1956 to solve this kind of problem. So the algorithm was conceived by Dijkstra in 1956 and published 3 years later. This is an algorithm that on first impression seems quite complicated and becomes far more intuitive when you've tried to practice on a few questions. But I'll just quickly talk through it and we'll try some examples. You label your start node with a permanent label 0. You assign temporary labels to all the nodes that are adjacent to the start node. You select the node with the smallest temporary label and make it permanent. You put temporary labels on each node that is adjacent to the node that has just been made permanent, making sure that temporary labels are the sum of the permanent label and the direct distance from it. If there is an existing temporary label at a node, it should be replaced only if the new sum is smaller. You keep repeating steps 3 and 4 until the destination node becomes a permanent label. And then to find the shortest path, you trace back from the end node to the start node and you write down the route and state the total weight. So as I say, in practice it is a little bit easier than it sounds. At each node we're going to be using this convention. We're going to have put this 3-box symbol. The top left corner is the order in which the nodes become permanent labels. The top right corner is the permanent label, in other words the distance to reach that node, and the bottom line is where we place our temporary labels. So back to the earlier example, we're trying to find the shortest route from A to F. So the first thing we do is to put the box system at every node, and I'll talk you through the process. The first thing we say is we're starting at A, so that's our first permanent label, and it has a value of 0 because we haven't travelled anywhere. If I travel from A to B, I can get there in 3 units, or A to C in 5 units. Now I know that from these 2 temporary labels that because 3 is the smallest temporary label, I can make that permanent. And it becomes my second permanent label. And the reason I know that this 3 is permanent is that any other route to B must go through C. And if I go through C, I've already reached 5 units, which is bigger than 3. So I know that this smaller value 3 must be permanent and the shortest way to get to B. Now you imagine being at B and travelling from B. So I could travel from B to D, which would be the 3 at B plus an extra 3. I can travel from B to C, which is the 3 at B plus an extra 1, which is 4. And if a temporary label is improved, you must show that improvement. Now I've got a temporary label of 6, a temporary label of 4. I can now make the 4 permanent, and it's the third permanent label. And I know that it's permanent because any other route other than A, B, C to get to C would have to travel through a 6, and a 6 is bigger than this 4. So the smaller value 4 can become permanent. You now imagine travelling from C. So I could travel from C to D, which would be an extra 1, so that would be 4 plus 1, which is better than 6. And I can travel from C to E, which is 4 plus 3, which is 7. And I'll look at all the temporary labels. 5 is the smallest temporary label, so I make it permanent, and that is my 4th permanent label. I know that I cannot get to D in under 5 units, so it must be permanent. I now imagine moving from this node D. So I could go to F, which would be 5 plus 5 at 10. I could travel from D down to E, which would be 5 plus 1, so that's 6. So that's an improvement on the 7. The smallest temporary label is 6, so that becomes permanent. It's my 5th permanent label. You now imagine travelling from E. The only place I can travel from E is straight to F, which is 6 plus 3, which is 9, which is a slight improvement on 10. The only temporary label I have now is 9 at F, so that becomes permanent. It's my 6th permanent label, and as soon as your destination becomes permanent, you can stop. So the route has a value of 9, so I know I can get there in 9 units. And the question is, how do we get there in 9? The best way of doing this is to trace back and say, how did we reach this destination at 9? Okay, so the way I got there at 9 was if I did 9, take away this 3, and I came here, which was 6. How did I get here at 6? That was 6, take away that 1, and I came from D, which was 5. How did I get to D at 5? That was 5, take away this 1, and I came from C, which was 4. How did I get to C at 4? Well, that must have been 4, take away this 1, I came from here, which was 3. How did I get to 3 at B? It was this 3, take away this 3, and I started at 0. So the route is A, B, C, D, E, F. So, example 2, we want to find the route from A to H with the least total weight. So we assign boxes, and again I'll talk you through the algorithm before we look at the clearer solution. So we're going from A to H. So A is my starting point, so I can make it permanent, and we haven't travelled anywhere, so it's 0 in distance. From A I can travel to B, and that would take 8 units. I can go from A to C, which would take 5 units. I now know for a fact that the best way of getting to C must be this 5, because any other route would have to go through a bigger 8. So I can take this smallest temporary label and make it permanent. So I can get to C at 5, it's my 2nd permanent label. You now imagine travelling from C. I can travel from C to B, which would be 5 add 2, which is 7. So there's a small improvement. I can go C to F, which is 5 add 10 at 15. I can go C to D, which is 5 add 4, which is 9. I look for the smallest temporary label, which is the 7. So I now know I cannot get to B in better than 7 units. So 7 is the best answer for B. It's my 3rd permanent label, and I now imagine travelling from B. Where can I travel from B? I can't travel to C because it's permanent, so the only place I can travel is B to E, which is 7 add 1, which is 8. You look at all the temporary labels, and the smallest one out of all the temporary labels is 8. So I now know the most efficient way of getting to E is 8 units. It's my 4th permanent label, and you now imagine travelling from E. I could go E to H, which would be 8 add 7. I could go E to F, which would be 8 add 3, so that's 11, which is an improvement on 15. I look at all the temporary labels. We've got a 9, an 11 and a 15. 9's the smallest, so it becomes permanent. So this at D, we have a permanent value of D. It's my 5th permanent label. And now you imagine travelling from D. Can't travel to C because it's already permanent. So the only place I can go is D to G, which is 9 add 1. I look at the smallest temporary label, which is this 10. So that becomes a permanent label of 10. It's my 6th permanent label, and I now imagine travelling from G. I can travel from G to F, which is 13. 10 add 3, 13, but that's worse than 11, so we just ignore it. But I can go from G to H, which is 10 add 9, which is 19, which is worse than 15, so we just ignore that as well. I look for the smallest temporary label, which is 11, so that becomes permanent. It's my 7th permanent label, and the only place I can travel from F is to H. That's 11, add 12 is 23, which is worse than 15, so we ignore it. And my only temporary label I've got now is this 15, so it becomes permanent, and it is my 8th permanent label. So we now know that the shortest path, the best path, has a value of 15 units. And how do we get there at 15? We start at 15 and we trace back. Where did that 15 come from? Well, that 15 came from 15 take away 7 would give it the 8 at that point. So where did the 8 come from? That 8 came from 8. If I take away this 1, I can travel from B, which was 7. How did I get to B at 7? If I took the 7 and take away this 2, I could have travelled from C, which was 5. How did I get to C at 5? 5 take away 5. I could have started from A, which was 0. So my route is A, C, B, E, H, with a value of 15. You can see the solution in more detail there. So there's my rough working, and there's the neater solution. So how does Dijkstra's algorithm work? The weights on the edges can represent different things. For example, they could represent the times taken to travel a stretch of road rather than distances. What do the temporary and permanent labels mean? They are the values of the quickest or the lowest route to that particular node. And the permanent label is the best value at that node. Why do we use temporary labels? The algorithm is systematically searching all the quickest routes to each node, and it's only when we've checked all of them that we can assign a permanent label rather than a temporary one. Later on in the algorithm you may get an improvement, so we can only use temporary labels until we're sure that we have the optimum answer, and that's why you need to use temporary labels. Why do we make the node with the lowest temporary label permanent? All routes up to a certain point have been covered, so the node with the lowest temporary label must be the next nearest node to the start, and it must therefore become permanent. What happens after this? You are certain that there is no shorter way of reaching that node. So you can assign adjacent nodes a temporary label from that node. Why does the first node get assigned a permanent label of 0? It is the starting point and you haven't travelled anywhere, so it's like resetting the clock to 0. Why does the method for finding the route at the end work? At the end of the algorithm, each node has a permanent label that represents the shortest distance to that node. If two nodes are joined, then the difference in their permanent labels will tell you the shortest distance between them. If the edge joining them matches this distance, then it must be the quickest route. So you're always working backwards, checking, does the length of the edge justify the change in the permanent labels? If so, that's the edge you need to use. It's not always necessary to label every node. You can stop when you reach the final node and it becomes permanent. That's when the algorithm stops. Dijkstra's algorithm can be used on directed edges. This algorithm finds the shortest path from the starting node to all the nodes that get permanent labels along the way. It is therefore not particularly efficient for the purpose of sat-navs. They use more complicated and heuristic algorithms to find the shortest route from the start to the finish. Dijkstra's algorithm is not as adaptable as some dynamic programming, which makes the best decision at each stage, so it does have one or two inefficiencies. Some of the common errors in Dijkstra's algorithm: not adding new edges onto the permanent label value, writing incorrect temporary labels and forgetting that you only replace them if it is smaller, not working from the last label which was made permanent, not realizing that when working back you can freely choose if two vertices are equally likely. In other words, they are both correct. You can have two possible answers. Some networks may have directed edges, and you can still use Dijkstra's algorithm provided you respect the direction specified along the edges. Occasionally networks contain negative lengths. Example, if you're talking about profit and loss or the costs on a particular route. Dijkstra's algorithm does not work if a network contains an edge with negative values. It would need to be adapted and changed. In the next session, we'll be looking at route inspection problems.